The Reykjanes Peninsula sits on a rift zone where the North American and Eurasian tectonic plates pull apart at roughly 2 centimeters per year. That motion is not uniform. It accumulates as strain in the rock until the rock fails, and when it fails on this peninsula, it fails with magma. For roughly 800 years, the Reykjanes volcanic systems sat quiet. Then, in March 2021, a fissure opened in the Fagradalsfjall system, and the ground began doing what the ground beneath Iceland has always done. It split, and basalt poured out. The temperature of that basalt as it emerged was above 1100 degrees Celsius. It moved not as a wall, but as a slow, pressurized fluid obeying gravity, filling every low point in the terrain, advancing in hours across distances that took geological processes millennia to form. By the time engineers in Iceland were looking at the lava field on satellite imagery, they had already run out of time to do anything about the fissure. The only question left was where the lava went next. The Fagradalsfjall eruption of 2021 was not directly threatening a town. It was threatening a road, and it gave Icelandic engineers their only chance to test something before a larger failure came. The Civil Protection Authority assembled a group called the Infrastructure Protection Group, engineers and volcanologists working in rotating shifts, and they built dams. The construction equipment available was 2 bulldozers, a CAT D9R and a CAT D10T, 1 excavator, and a vibratory roller. The bulldozers pushed volcanic overburden, aeolian soil mixed with gravel, into walls in front of the advancing lava. The material weighed between 1700 and 1900 kilograms per cubic meter. The logic was simple. Put enough mass in the path of a fluid moving under gravity, and you change the fluid's path. The walls were built in compacted layers, each layer driven over by the bulldozers themselves when the roller was not on site, because density is what resists the hydrostatic pressure of accumulating lava. A barrier too loose in its fill will fail not from the lava's heat, but from its weight. The first dam, the West Dam, was completed to 4 meters on the afternoon of May the 15th. The decision to raise it to 8 meters came on May 18th, when lava filled the valley faster than the simulations had predicted. On May 19th, Pahueho lava broke through the eastern lava boundary and moved toward the East Dam at roughly 0.3 meters per second. The construction team pushed emergency heaps onto the dam's crest using bulldozers, heightening it by 2 meters with loose, uncompacted material in a matter of hours. The loose material held the lava back that night. On May the 22nd, it did not. Pahueho lava overtopped the lowest sections of the heaps at the dam's west end, and within hours, a lava channel had formed over the dam's crest. By the end of May 22nd, the East Dam was buried. On June the 5th, the West Dam followed. The dams had delayed the lava's advance by up to 16 days. That was their value. Not permanence, not victory. 16 days. The lessons from those 16 days were written into engineering guidelines that Icelandic civil engineers would need again faster than anyone expected. On October 24th, 2023, an earthquake swarm began beneath the Svartsengi Geothermal area on the southern Reykjanes Peninsula. By November the 10th, 20,000 tremors had been recorded, with the largest exceeding magnitude 5.3. Ground-penetrating radar and GPS instruments showed the surface of the peninsula rising as a magmatic dike intruded laterally through rock at a depth of 4 to 5 kilometers. The intrusion was moving toward Grindavík, a fishing town of roughly 3,000 people. Engineers began building before the eruption started. The first barrier went up on November the 10th, 2023, the same day the earthquake swarm peaked. The target was not just the town. The Svartsengi Geothermal Power Plant sits a few kilometers from Grindavík and provides approximately 30% of Iceland's total geothermal heat and electricity supply. Losing it would not be a local disaster. The barriers were designed to protect both, and the two targets required different geometries. A barrier that redirects lava away from the power plant by channeling it into uninhabited ground north of town has to be placed upslope, at the points where the topography would otherwise allow lava to turn south and west. A barrier protecting the town itself requires continuous coverage along the approaches from above. The material for the barriers was the same volcanic rock that Reykjanes has been producing for 8 centuries. The cooled basalt from the last time this system erupted, now excavated by front-end loaders and trucks from fields adjacent to the construction zones. Trucks ran in continuous rotation, feeding material to bulldozers advancing the barrier line. The walls were built in compacted lifts, each roughly 1 meter high, driven over by the construction equipment before the next lift was added. Every meter of height added to a 25-meter-high barrier requires not just more material at the top, but a wider base to distribute the load. A wall that is 25 meters tall cannot have a base only a few meters wide. The geometry demands that the footprint expand outward in both directions as height increases, which means that raising a barrier by 2 meters along a 450-meter stretch requires thousands of cubic meters of additional fill, not dozens. The first eruption from the Sundhnúkur fissure system came on December 18, 2023. It lasted 3 days. The barriers held. On January 14, 2024, a second eruption opened a new fissure. That fissure ran directly through one of the barriers, not over it, through it. The ground split at a location the barrier had been built to protect, and lava emerged from within the defensive line rather than approaching from outside it. The barrier on either side of the breach redirected the flow into uninhabited ground, and the town was not destroyed, but the event established something that every subsequent engineering decision had to absorb. The fissures do not necessarily erupt from the crater system the engineers were watching. They can open anywhere along a dike that may extend several kilometers through the subsurface. A wall built to stop lava coming from one direction is useless if the eruption begins on the other side of the wall. The response to the January breach was not to abandon the barriers, but to reconsider their geometry. The engineering team began using HACRAS, hydraulic modeling software originally designed for river flow, calibrated with the measured viscosity and effusion rates of the Sundhnúkur lava, to simulate where a new eruption from each possible fissure segment would send lava under different flow volumes. The simulations gave engineers a map of vulnerabilities, not certainties. Every eruption changed the topography. Lava that filled a valley in one event removed the topographic low that had been routing lava away from infrastructure in the model. After each eruption, the team re-ran the simulations with updated terrain data from drone surveys, re-evaluated the barrier layout, and began reinforcing wherever the new topography created a new path toward the town or the power plant. The barriers grew. By the time the network reached its current configuration, it extended 13 kilometers in total length, with the highest sections reaching 25 meters above the surrounding ground. Eruptions continued through 2024. February 8th, March 16th, May 29th, August 22nd, and November 20th. Each event deposited additional lava against the barriers, raising the ground level on the upstream side. When lava accumulates against the face of a barrier, it does not stop pressing once it solidifies. The solidified crust becomes a new high point from which the next eruption's flow can begin closer to the crest. By late April 2024, lava had piled against certain sections of the L12 barrier to heights that were approaching the crest elevation. The engineering response was to move the line rather than raise it indefinitely. A geoengineer at EFLA described the decision directly. For every meter a wall rises, its base must widen and more material is required, and at some point it becomes more practical to establish a new line 120 meters back and start over. That logic produced a series of parallel barrier segments in the most heavily loaded sections, so that if lava overtops the forward wall, it encounters another wall behind it before reaching the town. In March 2025, lava breached Grindavík's defensive barrier and entered the town. Residents had already been evacuated. The geothermal power plant remained protected. But streets, pipelines and structures inside the town's perimeter were damaged, and the Blue Lagoon geothermal spa, operating nearby, closed again. The breach confirmed what the engineering team had been accounting for in its models but could not fully prevent. A fissure opening close enough to the town perimeter gives lava flow such a short travel distance that even a functioning barrier may not intercept it before the lava reaches structures. There is a minimum response time required to monitor a new intrusion, assess the fissure location, and determine whether existing barriers cover the eruption geometry. If the fissure opens faster than that assessment takes, the barriers are already in the wrong place. What Iceland has been doing on the Reykjanes Peninsula since November 2023 is not a permanent solution. The engineers say so explicitly. The barriers are re-evaluated after every eruption and rebuilt wherever lava has changed the terrain enough to open new flow paths. The geothermal power plant has continued to operate through 7 eruptions. The town of Grindavík has been partially damaged but not destroyed. Those outcomes are not the product of a system that controls what the volcano does. They are the product of a system that adjusts faster than the lava advances, fails at the margins rather than at the center, and treats each breach as data rather than defeat. The Reykjanes Peninsula will continue erupting. The magma supply beneath Svartsengi has been recharging between events since December 2023. Each recharge cycle taking weeks before the next intrusion. The ground rises, the earthquakes begin. The engineers look at the GPS displacement data and the lava simulations and move equipment to whatever section of barrier is most exposed. 13 kilometers of compacted volcanic rock placed by bulldozers and excavators working in rotation is the engineering answer to a rift zone that has been pulling apart for millions of years. It delays what it cannot prevent. It redirects what it cannot stop. Every eruption adds to the accumulated knowledge of where the fissures tend to open, what volumes they produce, and how fast the lava moves across terrain that is itself a product of previous eruptions. The only durable infrastructure on a peninsula like Reykjanes is the knowledge of what the ground is likely to do next, and even that is not enough to be certain.